Okay, this is the second day of 3.2, or day 5 on your homework guide. We're going to be talking about how the calculator calculates derivatives and also graphing with the calculator. They do something called a numerical derivative, and basically what the calculator uses is a symmetric quotient, which means that they're taking a point from the left and right of the point you want to take a derivative of at, and then subtracting the difference over 2h, because that's how far away it is. For sure, because it's going to be plus h minus a negative h. This is more accurate at the same values of h, and it's close enough to use on the calculator. The calculator uses an h of 0.001, which is called a numerical derivative. So this is what they use, and I'm going to show you that if you calculate it by hand and how close this gets to a derivative. So if this is the function f of x equals x cubed, I want to use the numerical derivative to find f prime of 2. So I want to know what the calculator would say. So the numerical derivative would equal, and the reason we keep saying numerical is because we're using 0.001 for h. And when I put this into my formula, the function is at 2, so it's 2 plus the change cubed minus 2 minus the change, all over 0.002, because that's 2 times h. If you type this in and calculate it, you get 12.000001. And sure enough, the actual derivative is 12. So it's accurate to 5 decimals. So let's look at how you do this on the calculator. Basically, if you have the new math print, you can clearly see what you do. So we're going to type this in. First of all, though, you go to Math, and then just go down to, I believe, number 8, which says nderiv. And there it is. This is basically the numerical derivative. So you hit enter. If you have math print, it's going to set it up for you. We're taking the derivative with respect to x of the function x cubed, and I want to evaluate it when x is equal to 2. So that's what you plug in. We're taking the derivative with respect to x of x cubed. These should match, these variables, and then you tell it what number you want it to be. You hit enter, and sure enough, we get the same 12.000001, because that's what they use to calculate it. Okay? Now, if you do not have math print, real fast, let me put that on here as well. Turn it off so you guys can see the classic version of that. It works the same way, but if you do not have math print, if you have like a TI-83 or an 84 that does not have math print, you do the same thing. You go to Math 8, and instead of that whole in the symbols, you'll just get nderiv parentheses. All you do is type in the function, and then the variable you're using for the function, which is x, and then where do you want to evaluate it? I want to evaluate it at 2. You hit enter, and there's the same thing. Okay, now most of you guys will have the math print, so I'm going to keep working with the math print version, but this is how you would do it without the math print version. Alright, so now, one thing that is important though is you cannot do this difference quotient at a corner or a cusp or a vertical tangent. Because we know that when y is equal to absolute value of x, we have a V-shaped graph and there's no derivative at this point. However, the calculator doesn't really know that. What the calculator does is they take a point just to the left and they take a point just to the right, and they find the slope between those 2 points. So on an absolute value graph, notice how I kind of drew that in. It looks like a horizontal line, so it would probably estimate it at 0. And sure enough, when you do Math 8 and you type in the derivative of the absolute value of x, where's absolute value? Number. Okay. We want the derivative of the absolute value of x right at 0, where there's a corner. So we're going to see what the calculator tells us. And the calculator tells us it's 0. So you have to be careful. You have to know, is that a is it a point of non-differentiability, or is it or can we take the derivative there? because the calculator does not know. That's why it's important to note before you actually use this. You cannot use it at corners. That should be an undefined or a no derivative. Okay, so here's how you graph it in your calculator now. Let's say we want to graph the whole thing. Okay, I'm going to pull up my graphing calculator. I'm going to type in natural log of x into my calculator, and I'm going to make my window go from 0 to 10 instead of -10 because there's no value. So that's the natural log of x. Now let's say I want to see the derivative of that. It's the same thing that we just did, except for one slight change. I want the derivative for y2. So I'm going to go to Math 8, and I'm going to type in, I want the derivative with respect to x, and I want to do it, you can either type in natural log of x, or you can just go right to vars, move over to yvars, hit enter, we've done this before, and pull up y1. I want the derivative of y1. And here's the other change. Instead of at a point, I want it to graph the whole thing. So I want for all x's. So sure enough, I graph this. There's my natural log of x curve, and now there is my derivative. Okay? Notice the derivative looks like it has an asymptote at 0 and a horizontal asymptote at 0 as well, an end behavior asymptote. This looks like half of our function y is equal to 1 over x. And sure enough, but again, it's only when x is greater than 0, it looks like that. And it actually, that is the derivative of natural log of x. Now, just some analytics for this. Notice that the derivative is never 0 because it never actually plateaus, but it gets close as this goes along. Notice also that the derivative is always positive. It's very positive up here. Remember, this second graph is the graph of the derivative, which means that it's increasing a lot at this point for the graph, which looks correct because if you drew a slope of a line right there down here, it would be very positive. So we put a point there. As you move along, though, this slope is very small, so that's why this graph of the slope is getting close to 0. Okay, let's do one more of those. What else did I have on the list? Let's do cosine of x. Now with cosine, let's change the, and you can keep your y2 the same, which is kind of nice. So I'm going to say cosine of x. This is why it's good to use y1, because then you don't have to change that. I am going to change my window to just look at maybe 2 cycles of this curve. And then I'm going to make it go from, it only needs to go from -1 to 1. Okay, so the first curve that's graphing is cosine, which you guys should know because it hits the top. So now this is the derivative. And notice that when you start at 0, it goes down first, and then back up, and then finishes at 2 pi. That, hopefully you guys realize, is a negative sine curve. Okay? It's a negative sine curve. So we would say the derivative looks like a negative sine curve, which it actually is. You'll find that out later. Again, some things of note. Again, this is the first one. Notice how the cosine graph at the top, at the max, the slope of the line there, if you draw a line across, would be 0, and sure enough, the derivative crosses at 0. Also note that in this whole region here, the derivative is above the y equals line, which means the derivative is positive, and that is going from this spot to this spot, and sure enough, the graph is increasing because the derivative is positive. So, important stuff to note, and then the same for negative on graphing and knowing how to type that into your calculator.